welcome to day 9 of the 12 days of LiDAR. My name is Alex Billick, and today the topic is going to be on the LiDAR package or lidR package within the R stat suite. There's some great resources available for this as well, just like with Fusion. I'd point you towards the tutorial book, the GitHub, and the documentation. We're going to review all three of these. But I want to give you some background on this. So, R, if you're not familiar with it, is a stats package that has been extended now into the sciences and is incredibly flexible. So you can use it for GIS, remote sensing, lidar, stats, all kinds of different utilizations, and it's extended by way of these packages. And so this lidar package, when it was released, and I had to look back here. So the public release to the CRAN repository was December 31st, 2016. And to think that this package has only been around that long and how consequential it has become to LiDAR processing is pretty incredible. This was funded by the AWARE program out of University of British Columbia, and now has been funded, I believe it's from the Quebec government, making this freely and openly accessible with some truly amazing tutorial materials available, and documentation as well to follow along with it. So if you want to check it out, I'd recommend you start with, you can go to the GitHub page, and if you find yourself here, you know you're in the right spot, and then you can click on the link for the book if you don't want to try to remember how to get there. But this is step-by-step tutorial material explaining how to read in data, how to validate your LiDAR data, all the different algorithms, all the different background on it. It's extremely comprehensive. If you don't know R at all, I would highly recommend that you maybe check out some kind of tutorial in R first. You don't have to know R to use this because the tutorial material is so comprehensive that you can kind of figure it out along the way. But a background and an understanding how R defines variables, how it handles things, um, would be useful for being able to extend your knowledge and skill set in this area. But what can you do in LiDAR? We're going to go through some sample data sets, but they outline it very well here. So you can read in a single tile. You can also read in an entire catalog of tiles and deal with it for an entire land base, as you see here. Canopy height model, DTM creation. You can chase individual tree segmentation. But it's this wall-to-wall dataset processing and the idea of a LAS catalog that really makes this a powerhouse when it comes to large sets of data. I've processed probably at this point hundreds of thousands, if not millions, of tiles of LiDAR using this package. It's very versatile, it gives a lot of flexibility, and it accounts for things that are easy to miss. So things like we don't want to just calculate a DTM for an individual tile. We want to make sure that we understand what the terrain is doing around that tile so we know which way is water going to flow. Simple things like that, you have that ability to account for those. So the documentation is here, the background information is available as well. And then if you want to get into understanding some of the function documentation, this does ship with it as well. But the package information from the CRAN website is also available. So let's jump into R. R is the way to install this if you've never used it before is you install R and then you can either run things directly in there, or I'm using a tool set called R Studio, which is a little bit of an easier interface. So this is sitting on top of the R software itself. So I'm running the latest version here, and I've installed the lidar package. And here's what the help documentation looks like for it. So we can look at every single function. Let's go down to something like point metrics. Pixel metrics, sorry. So pixel metrics, it'll explain what you're going to do with it. It'll explain everything and give you all the different layouts for how to actually create those code to be able to use it. So what we're going to do is I'm just going to run this live and we'll see how it goes. So the first thing you do is define your library. So I'm calling in lidar. If it wasn't installed, you'd have to install it. And then I'm going to just define my LAS file. So this is coming mostly from that tutorial book. I'm just giving you a high level view of what it looks like. So I'm using a lot of the same syntax that they had. If you want to follow along and do this yourself, just pay attention to the direction of the slashes. That's an easy thing for someone not familiar with LiDAR to make a mistake with. So now we've read it in, let's get some information. So I can get projection information here, the area, the point density, all that information directly from it and see which version of LAS it's using. Then I can go through and actually do a LAS check on my LAS object. So there's some overlap and some other scenarios here going on in the data directly from the ministry. So we could do some cleanup there if we wanted to. I'm just going to kind of motor through this so that you can get a sense of what's possible, and then you can dive into it in more detail. So I'm going to plot it. It's opening an external viewer there. I'm just going to give it a second to populate, and then I'll drag it over onto the recording area so that you can see it. This is not going to be as smooth as other 3D viewers are. It's a functional one. You can use it to see if there's any major gaps or issues, but it's a little bit slower than everything else that I've showed you as a generic viewer. But you can identify quickly if you grab the wrong tile. It's a handy tool set for that. So we're going to take a look at it. Zoom around a little bit, and then we'll close it. So now what we could do is we can actually add in things like labels and axes. So what I'm going to do here is pull the scan angle directly from the LiDAR, and I'm going to plot it so that we color code the different scan angles, and we can see in this particular tile how those scan angles varied. So there's that again. It's populating, so we got to let it finish before we try and move it around. And there we go. So we can gain some insights into our data. That was just one example of a variable. If you wanted to plot different things, what you want to do here is just click the little arrow next to it, and basically any one of these you could have it populate. I was going to do classification, but it takes a long time to draw that in, so I'm just going to skip that for now and go straight to generating a digital terrain model. So what I'm asking it to do now, I'm just going to close that, is to basically take the terrain and rasterize it. So this function is documented over here if we wanted to. It's thinking. So it's going to compute a DTM layer for us. And we're using a 1 meter resolution here for that. Okay, it's completed. So now what I can say is plot DTM tin, and there's a 2D plot of it. We can also, if we want to plot this, we can use a 3D DTM viewer. Bring it up here. And it generates a quick hill shade for us. This is a lot faster than moving around the point cloud. So again, similar to what you saw in QGIS, but we're running it all in R now. Now what I'm going to do is I'm going to generate a normalized last cloud. So I'm basically going to take the last point cloud and subtract the digital terrain model. And it's finished. There are a lot of different ways to do this. I'm just generating this as a way to show you how to work with the tutorial book if you're interested in learning this more. Again, it's drawing it in the 3D viewer here. Once it finishes, there's our normalized point cloud. Reason I want that, there is going to be some noise. It's usually around the water there, but we should be okay. Is I want to then use a point to raster function to generate a canopy height model. And it finished. And there's our canopy height model generated. I'm not filtering for buildings or anything like that. I just want to show you how easy this workflow can work. Now what we're going to do is something a little different. And this would take more calibration and time, and I generally wouldn't be running this on the image of campus here unless I did some building filtering and some other work to this first. But what I'm doing is asking it to identify individual trees. It's going to generate a ton of noise here. This is not how you would actually run this, but I want you to see the fact that you can do this kind of work to try to chase ITC or individual tree classification using R. You would change the window size, you would classify buildings, you'd probably remove them and just focus on the vegetation class and then run this, but just want to show you what's possible. Okay, so we're going to plot this. So what this code is doing is drawing our canopy height model, and then it's going to drop all of those points on top of it. And you see that we end up with a lot of points on buildings, but a lot within the trees as well. We could drop this into 3 dimensions as well, but I'm going to skip that for now. The last thing I want to show you here is how we generate a suite of standard metrics. We're going to use the pixel metrics function here. And so we're pointed to our normalized LAS, and then we're going to calculate our standard metrics at a resolution of 20 meters. So that's going to be quite coarse on this, but the intent is if we were doing this on thousands of tiles to be able to generate an area-based inventory, what would that look like? So I'm going to have it sit here and compute that. Once it's finished, we can just type in metrics and see. So it's a raster, our dimensions of that raster, the extent, and all the different variables. Then I'm going to call a library called raster. This is another package, which what it lets me do is write out a raster. So I'm going to say write raster, and I'm going to open up QGIS, and I'm going to drop our newly created metrics TIFF into it. And what you want to do when you're working in Q is go to properties, change it to single band. You can make it single band gray or single band pseudo color, it doesn't matter. But now all of the names of these bands are the metric that was just calculated for your LiDAR. And those names you can find in the documentation. So if we pull open documentation here, sorry, there we go. You can actually see, so the skewness of height distribution, the standard height, the mean height, max height, all within those raster cells. So we can very quickly generate wall-to-wall metrics that we then would apply our plot to LiDAR models that we built using our area-based methodology. This is a way to build the landscape level metrics that we could then apply it to. So if we want to look at, say, the mean height, why not? Then you get a sense of it here, and we can actually query this and get individual raster cell values here and get all of the information if you want. So it's extremely powerful. I have just skimmed the surface of what the LiDAR package can do, but it shows you how quickly it can do this. And what's really cool is if you explore this with that tutorial book, especially on the LAS catalog, you would be able to apply the same knowledge across hundreds or thousands of LiDAR tiles and scale this up. Once you start getting into that, then I would highly recommend looking at packages like tidyverse to help you structure code so that you can pass variables and build projects that are relative within the same folder structure. So there's a lot of things that you can do to extend this further on, but I'll leave that for you to discover. So with that said, I hope that you found this interesting. I encourage you to start to learn this package if you're not familiar with it at all. And thank you very much for listening. Tune in tomorrow for LAS tools and LiDAR.